Okay.
Okay, so we'll do the introduction. So thanks all of you for joining this talk, and of course those of you looking at this video from our YouTube IAU-J1 channel. Thanks so much for watching. It is today my absolute pleasure to introduce Dr. Alexandre Vazdekis, a friend and colleague from our Instituto de Astrofísica de Canarias in Tenerife in Spain. Our speaker is a very well-known expert on stellar population synthesis. His models, based on the Miller Stellar Library that have been produced by his group and have also extended versions, they have been adopted by a very large number of researchers in our community, with the Miller's models website exceeding 250,000 visits. Beyond the development of synthesis models, he has worked on the formation and evolution of early-type galaxies, including chemical enrichment, the role of the stellar initial mass function, among other topics. Dr. Vazdekis got his PhD at La Laguna University, with postdoctoral jobs in Durham in the UK and Tokyo in Japan, returning to Tenerife, where he joined the faculty at the IAC in 2008. So we welcome and thanks so much, Dr. Vazdekis. He will give us a seminar on expanding the predictive power of stellar population models. So thanks so much, Alex. The floor is yours.
Yeah, good morning, or good afternoon, or good evening. Thank you very much for your introduction and for this opportunity to present our work on developing stellar population synthesis models, as you mentioned. Well, these models have been, as you know, instrumental in painting our current picture of how galaxies form and evolve. In fact, they provide among the strongest constraints so far to the numerical cosmological simulations. And well, I will start by basically summarizing some of the key results from this analysis, and then move on to the new developments that I would like to we are working on it that we would like to share with you. Okay, so well, thanks to the stellar population models and the stellar population analysis, we have been able to conclude that there are a number of trends followed by early type galaxies. Here, for example, you can see the trend with mass, galaxy mass, in the sense that older, more massive galaxies are older and more metal rich. In this plot, you can see that on the left, I think you can see the cursor. Okay, going down means that it's older, and moving right means that it's more metal rich, and more massive galaxies are as old as the universe and, of course, supersolar metallicity. It is well known, for example, that also the abundance pattern of these massive systems are not is not similar to the one of the Milky Way. So, for example, it's well known that the magnesium, as you can see here, is overabundance with respect to iron in comparison to the solar scale mixture. But it's not the only one. There are other indices that also show this departure with respect to solar. I will show you some later some results about that, and basically indicating that these galaxies, particularly the more massive ones, form in shorter time scales. This, let's say, the early type galaxies that we see today, okay, in the nearby universe, these are the local fossils, in a way, the direct descendants of the massive galaxies that, for example, the James Webb Space Telescope is finding at Z above 3, all suggesting these very recent results and impressive results that these galaxies are very old. You don't need to be an expert on stellar population synthesis, or by looking at this spectrum for example, of a galaxy, a redshift 3.2, you can see that it's rather old. It's very red, right? So it's all these results suggest a formation epoch well beyond Z3. And this introduce a tension with the cosmological numerical simulations. Here, for example, is the same plot I showed you before, but now this these black points, okay, represent thousands of galaxies. Okay, these are stacked spectra of galaxies at redshift 0.4, and the bigger the symbol, the more massive the galaxies are. So, for example, this big one is 300 kilometers per second, so 11.5 in log m, and this one, so you can see that now the numerical simulations in orange, okay, they spread all around and much younger than the observation. And this is roughly because the star formation histories predicted by these models are, let's say, as you can see here, more extended over time, and it should be, according to the observation, something that very an early epoch and little recent star formation. In the recent years, especially in the last 15 years, there have been a lot of advances, for example, regarding the initial mass function. For example, the initial mass function is no longer considered universal. This has been a big, let's say, impact in the community. And here, for example, I'm showing you the mass fraction of M dwarf stars as that has been estimated, okay, from galaxy stacks of thousands of galaxies, as a function of the velocity dispersion. And you can see that, for example, that smaller galaxies, like, for example, the Milky Way, they contain a fraction around 30% of M dwarf stars in a mass fraction, not numbers. And then in the massive, most massive elliptical galaxies, you find a fraction that easily double that. I mean, sort of above 60%. And this has been confirmed by dynamical studies and other approaches as well, although there are still some tensions with some other works like gravitational lensing. This, let's say, call it bottom-heavy feature is mostly localized in the center of the galaxy, as you can see here. Okay, the center of a massive galaxy is very steep, the IMF, which means a bias toward smallest stars, and then drops when you get, for example, and gets to normal. I mean Milky Way-like when you reach the effective radius, and this has been confirmed by several authors over the recent years. There are also results that are coming from opening, because so far most of these results have been obtained from the optical window, but if we keep opening, let's say, the spectral range where we are working with, it gives us more hints on the constituent stellar populations. If we open to the ultraviolet spectral range, basically, you can see here the HR diagram, okay? So basically, we only care about the hottest stars. For example, the ones on the turn-off, or hot horizontal branch, or whatever they mean, only the hottest stars. And we don't care so much about the cooler stars. Here is, for example, in the bottom panel is one of the stacked spectra that I showed you before, in particular very massive one, which is in black, okay? And in red, you can see the spectrum of a old population as the ones we were inferring or estimating from the optical range. Okay, so you can see that all the light that we see in the optical range is basically, this red line is basically matching the black spectrum. Okay, it's a perfect representation in the optical this old population. However, if you move to the ultraviolet, you can see that the black line, the black spectrum is departing from the red spectrum. Okay. Now, if you add a young component, a very tiny fraction of a young component, 1 per thousand, okay, 0.1 percent, okay, which is the blue. This is a blue model, okay, a young model around let's say 0.1 gigayear old. You can see that the light in the optical is completely negligible in comparison to the red. But if you go to the ultraviolet, you can see that it dominates clearly the light there. And then if you have this component on the top of the old component, then you can match the full spectral range of this galaxy stack. However, this is not the only explanation. There are other scenarios that need to be tackled, and one of them, for example, is the contribution from hot evolved stars, which can also make the same kind of, let's say, good fits, okay, to this spectral range. But what is really important is to analyze the two spectral range simultaneously, and not only one of them, okay? So in doing so, you can see here, for example, some of the index measurements. This is again H beta O, which is the optical and H indicator, and this is the magnesium iron combined index, which is a global metallicity indicator, and the lines and as represented as a function of H, okay, and these are the stacks of different masses, of course, becoming the bigger symbol becoming older, because and more massive, as you can see in this the picture that we get from the optical that we discussed before, right? So, but if you look, and they match very well with a single population, okay? For example, this continuous line that you can see here. However, the same, if you look now in the ultraviolet indices, we can see that they are far from the single populations. You can see that they are far from this solid line or dashed line, okay? They are, however, if we introduce like a tiny fraction, okay, like shown in this model, no? This is the, let's say, in the last, say, 1 gigayear or 2 gigayear, okay, population, and you get like a contribution around 0.5%, okay, then we match very well all the indices, both in the optical and in the ultraviolet, okay? Suggesting that these galaxies, despite the fact that they are all passively evolving, okay, they are not completely dead in that sense, but it's tiny. I mean, it's not changing the picture, but it's relevant to know this information. If we now move to the near infrared, which has advances in the last years, now if we look at the the HR diagram, now we don't care anymore about the hottest stars, but we care about the coolest stars, because they are the redder and the ones that they shine most in this spectral range. And if we compare these recent model developments with the observations of these massive galaxies, we find, for example, look at the CO are 1.56 micron, and you can see that the observation, the spectrum of these massive galaxies provide very deep, very strong CO features, which cannot be reproduced by any model you may consider. Okay, these are the lines, let's say, of different colors representing these models. Okay, and you can see that this is in the H band, several CO indices in the H band, all of them behave in the same way. But also in the, for example, look at here at the CO at the 2.30 or 2.32. Okay, the same story. Okay, it's a strong feature, and I would say that this is perhaps the biggest challenge posed to the stellar population modeling so far, at least in the near infrared. There has been several attempts to match this feature, and but it's not possible, and it cannot be done with intermediate age stellar population as it has been suggested by even in some of the previous works. If we look now at dwarf elliptical galaxies, you can see here the magnesium over iron versus the metallicity, or the sodium over iron versus the metallicity. Okay, and well, these blue points are the Milky Way stars. Okay, you can see the typical pattern. Which is, for example, magnesium enhanced in the low metallicity, and if we look at solar metallicity, they are scaled solar, right? And the black symbols here are the dwarf ellipticals, and these triangles, these red triangles, are the giant ellipticals. And you can see, for example, how in sodium the giant ellipticals show an excess of sodium over an enhancement of sodium over iron, but dwarf ellipticals show a de-enhancement of sodium, and the same applies also to that. You can see here the magnesium over iron is not following, let's say, the abundance pattern of this the Milky Way, nor the giant ellipticals. It has been also these models have been applied to the recently discovered massive relic the so-called massive relic galaxies, which are compact galaxies that resembles the galaxies, the red nugget observed at Recife 2, and which are very compact, as you can see in this luminosity, the surface brightness profiles, okay, and well, the analysis of their spectra show that they are very old, okay, no indication, as you can see in the derived star formation histories of young populations if you look from the optical range. So they're completely similar to the magnesium iron enhanced, the metallicity very high as well, and so they're very similar to the giant elliptical galaxies. These are thought to be like this, like the cores of the ellipticals. The present day ellipticals are redshift. Okay, so so very consistent with the two-phase galaxy formation scenario, where first they were forming in situ and then start to grow up by accretion over time, and these galaxies, the ones that we see in the local universe that are very rare, counted ones, okay, are in a way they didn't go to the second phase. They stayed only in this, let's say, in situ dominated formation. If you look at the IMF, is also similar to massive elliptical galaxies, okay, very bottom heavy feature, and if we look at the ultraviolet, okay, we see that we get similar fractions of young stars as in the other. They are very tiny, of course, but very similar to the ones of the massive galaxies. And if we look at the infrared, at the CO, we can see that for example, this is green. The green line is 1277, which is the prototype Rayleigh galaxy. Okay, is very similar as well as the massive ellipticals. And of course, I didn't want to finish this introduction without forgetting that we are entering the era of the machine learning and artificial intelligence that is starting to, let's say, allow us to apply these techniques for fitting our spectra, galaxy spectra. And I got to say that well, the first experiments, let's say, to photometry, to line indices, or even the spectra, fitting the full spectra, are showing results that are pretty much consistent with our standard approaches that we've been using so far. So this is really like opening a new potential here. Okay, so let's now move on, and let me give you like a small description how these models are built. So basically, the basic thing we could do is what is so-called the single stellar population, which means single burst, single age, single metallicity population. If we manage to build such a population, then we can, of course, make much more complex populations, like, for example, with resembling, let's say, all variety of galaxies. The stellar population is basically needs three main ingredients. The first ingredient, if the state of the art of the stellar evolution theory, okay, which is summarized in the isochrones. There have been a number of groups working and continuously developing these models. And the stellar libraries, the spectra, which can be either theoretical or empirical, and all having advantages and disadvantages, okay. And of course, we need to assume an initial mass function, okay, in order to assign the numbers of stars to the isochrones. In doing so, if we integrate along the isochron, we basically obtain we have an output, the spectra. We can have photometric colors, mass to rate ratios, line strength indices, spectra of varying resolutions, and even recently surface brightness fluctuations. And in a way, these predictions show the kind of the evolution over time of this modeling. And here I have shown you, I show an arrow that goes, this arrow you can consider is the arrow of time, okay? So first models predicted photometric properties, then moved to line strength indices, low resolution spectra at moderately high resolution, and finally surface brightness fluctuations. When we compare these models, different, let's say, models in the market, okay, well, seems that it worked quite okay in the optical range, as you can see here, for example, several models, well, they more or less is not one-to-one, but it's a reasonable agreement, let's say, as expected. For example, here comparing our models, which is on the vertical axis, with the Brusois and Charlotte models, the Conroy and Vazdekis models, Maraston models. However, if we look at the near infrared, the situation changes. There's far more disagreement. Okay, sometimes very strong disagreement, as you can see in this. So you can see that they are departing significantly from the one-to-one line, and this is very well illustrated when you compare with the globular clusters, in this case extragalactic and Milky Way globular clusters, and you can see these different colored areas represent different models, and you can see that the predictions, they differ significantly. Particularly in the bottom panel, where you can see for example, the Paschen beta at 1.28 micron, okay, versus in this case versus the magnesium iron combined index, and not so much in the optical, as you can see in the upper panel, the H beta O indicator. Now there's another important model development that has been, let's say, representing a significant advance in the field, which is the consideration that the varying abundance ratios in these models. I'm following this scheme that the base models, which are, let's say, the standard models that we don't care at all about the abundance ratios, okay? Basically, we combine empirical stars, which basically follow the abundance pattern of the Milky Way, with scaled solar isochrons, Okay, this has been, let's say, the standard approach as far as we do not consider the abundance ratios. Now, there are also models that have been developed that base it fully on theoretical spectra with varying abundance ratios, and also models that are based on the empirical stars but corrected differentially with theoretical spectra to accommodate these abundance ratios variations. Well, this can be summarized here very well. This is the abundance pattern corresponding to the Miles stars, which is the standard, let's say, one standard reference in the optical range, the library. And well, it's nothing special here. It follows completely the abundance ratio of the Milky Way. So you can see that it goes below -1, it's alpha enhanced or magnesium iron enhanced in this case. And if we go to this solar metallicity, then we get to the scaled solar regime, right? So, but galaxies, as we discussed previously, they show that they are not following, they're not matching this pattern, okay, they're deviating. So, for massive galaxies, we would like to travel up, okay, get enhanced populations in magnesium over iron, while for dwarf galaxies, we need to go down. Okay, in the metal pool regime, we need to go to the scaled solar regime, for example. Okay, so, and this is the challenge. And as I mentioned before, this can be done, or it has been done, with empirical stars or with theoretical stars, and it's always the discussion which one of which approach to follow. Okay. And well, what I can show here is that, well, it depends what's the purpose, what's the, I mean, the application. And here is a model built with my code, okay? So everything is the same, but only substituting the library. In one case is Miles, I mean the empirical library, and in another case is a theoretical library. Okay, so in the upper panel is the scaled solar. Okay, so, and this is an age of 10 gig a year and a solar metallicity model. Okay, so I can compute a model with a based 100% on empirical stars. So, and this is the ratio between the two. Okay, again, everything is the same. The only thing that changed is the input stellar library. So you can see, for example, that the magnesium here is going down, but then the iron lines goes, you know, so you get that the magnesium and iron lines, they oppose as expected. But in this case, is basically, you know, what you can see is the differences due to the models. Okay, this theoretical versus the empirical, and you can see that especially in the blue, the differences are really strong. And the same applies at the metal poor regime with alpha enhanced, let's say, stars, either theoretical or empirical. You can see that there's an issues going on the Balmer lines and so on. Okay, so we in the last year we are developing the S-Miles project, okay, to develop a new stellar library and SSPs with these varying abundance ratios. So we computed a theoretical library with the state-of-the-art, let's say, models, and line lists, updated line lists. So, and as you can see here, these are some of the stars, okay, as with varying temperatures and in the different panels, okay, and varying metallicities and gravity. And we were plotting these theoretical stars on the top of the observed star, okay? And this is the ratio between the two. You can see that there are significant differences between these theoretical stars, despite the fact that they are state of the art, okay? And the observation, I've got to say that there has been a significant improvement over years, okay? But as you can see, there are significant differences as well. So we're not going to use this theoretical spectra in absolute terms. We are going to use the differential corrections. We are going to see, let's say, this is the ratio between the alpha enhancement of 0.2 versus scale solar. Okay, so well, is the correction, as you can see, are smaller, significantly smaller than what the difference that you can see here between the two. Okay, between the let's say when you just want to match an empirical star, okay, with the theoretical star, you can see differences that are much higher. It can be 100%, okay, differences, while here we are talking about 10%, or so. So, and we are taking only these differences in order to correct the empirical stars. So, for example, this is the one case, illustrative case of a star that is alpha 0.4, okay? So, of course, you don't need to apply any correction. Now, if you want to make a star of 0.2, 0, or you vary the abundance, or here is even de-enhanced, okay? Then the idea is to apply these differential corrections, okay, to the empirical ones, and like this we get let's say in this case 5 stars with varying abundance ratio, but based on these empirical stars. In the end, we construct a library, which we called it semi-empirical Miles library, S-Miles, okay? So in the end, we end up having 5 libraries, S-Miles libraries, with where all these observed stars were bring to different levels of abundance ratios, you can see as indicated in the y-axis, okay? And these then libraries are employed to build up the stellar population models, the SSPs. And here, what I am showing you is the ratio between different, between the same SSPs with varying abundance ratios divided by the scale solar model. And you can see here that the corrections increase with decreasing wavelength, okay, and you can see that this difference, the residuals that we see here are much larger when we depart more from the scale solar, as expected. You can see here on the right panels, for example, the iron line, okay, and different with this is different enhancement these are SSPs, okay? Or we can see that the magnesium here, you can see that they go the opposite, right? You can see, for example, that the blue line is here, and this brown line is here, and here is the other way around, okay, for the magnesium triplet line. And these differential corrections are much safer than, let's say, than using the fully theoretical spectrum, but they are not immune to. There are differences that are maybe non-negligible differences depending on the models we still use for deriving these differential corrections. So here is, for example, an illustrative example. It is H beta, okay, in the upper panel, and H beta optimized, which is another definition of this index value, of this index, as a function of H. And here are the S-Miles predictions with our original models. Here you can see in the upper panel that there is the two red lines. These are 0.4 enhancement are for scale solar. Okay, they're basically the H beta is insensitive to the abundance ratio. However, in the new models, in the S-Miles models, you see a significant sensitivity. Now, if we use a different definition of the H beta index, okay, you can see that is the other way around. So you can see now that the S-Miles, the H beta O, is insensitive to the abundance ratio in S-Miles models, while H beta is sensitive. Moreover, the dependence on the abundance ratio goes in the opposite sense. Here, for example, it goes up, and here the black lines, you see, goes down. So this, of course, has an impact on our let's say diagnostic diagrams that we often use for inferring these populations. Okay. There are, of course, some caveats that I would like to draw your attention about, which is we've got to be a little bit careful when using indices based on molecular lines, particularly, for example, the magnesium 1 index. That, for example, you can see here that for solar metallurgy models and different ages, okay, this is becoming this pink is the oldest age, and the blue sequence here is corresponds to 2 giga-year population, and it decreases with increase in alpha, which is at odd what one would expect. Okay, so these are difficult to model, and all what I want to say is that the best use of these models to understand the lines or the features that work better, okay, and restrict the analysis to those features. This is my suggestion. Moreover, if we have, for example, like in our original models, two means, okay, 0 and 0.4 enhancement, say in alpha, well, roughly, I mean, when you interpolate, because you want to, when you're fitting your galaxy spectra, well, basically it's a linear interpolation, but this might not be the case, as very beautifully illustrated here. This is the magnesium B in the bottom panel as a function of the enhancement, okay, and in the new models we have more points, more beats, and you can, and here we have 0 and 0.4, okay, and well, it's not too far, let's say, from being linear, but it's not completely linear. So it's an advantage of having varying beams. And of course, there are indices that are almost virtually insensitive, okay, to the abundance ratio. For example, the magnesium, both the magnesium iron combined, or magnesium iron is another definition of this index, which is the magnesium iron combined prime. Okay, you can see here for this age, or for this, for example, for 14 gigayear-old, okay, populations, that it does not vary its strength with increasing abundance ratio. This is particularly important when we only care, for example, about the age or the metallicity, the total metallicity. Well, at least it's a starting point if we want to deepen in the abundance ratio later. Another area of development is, I mean, and this is very important, I mean, if we want to change the abundance ratio of our models based on the empirical stars, we first need to know the with the highest precision possible the key abundance ratios, okay, of our of the stars of the libraries that we are using, for in this case the Miles and the Excel libraries. So this is another project we embarked on in the recent years. So and here, for example, the determination for the Miles library, the Miles and its extension, its resonance extension with 200 additional stars, and we determine it in a homogeneous way by fitting with theoretical spectra, the ones that I explained you before, to infer the abundance ratios in a proper way. And you can see here the patterns that we derive as expected, of course, but now we know for every single star its abundance ratio. The same, we're extending this to other elements like also calcium, using the calcium triplet lines, as you can see in the plots here, or in the bottom panels you can see how the fits are to the magnesium line or to the calcium, one of these calcium line, particularly the wing of that line, okay, to avoid non-LTE effects. And this allows that to determine the abundance of calcium over iron, magnesium over iron of the stars of the library. Okay, so this is and you can see that we get this value from where we can start now building in a robust way these models. Another development, very important development, is the increased spectral resolution of the models. And this is an initiative of what we called it WaveLive, because it's the library that will come for free from the Wave Stellar Library project. We are not going to observe, to make specific observations to but to, let's say, enjoy the observations from the different surveys within this collaboration. This library is basically we are assembling stars stellar spectra, I mean, from the different surveys like the galactic archaeology or massive stars, and both from star-targeted surveys, but also from galaxy-targeted surveys, because thanks to the 2-degree field of view, we will always get the stars in the field. Okay, so even when we observe galaxies, we can still take benefit of these observations to include even more stars. The resolution is increased to 5,000. Okay, we are going to use the low resolution mode, and just to compare, the Miles library is 2,000. So we are increasing significantly. This is particularly important for analyzing objects like the dwarf, low velocity dispersion galaxies in general, okay, even global clusters as well. So the spectral coverage is going to cover all the optical range up to 1 micron almost. And importantly, the parameters, star parameters of the star will be obtained homogeneously, and we're going to take benefit of the footprint of the survey to include many, stars of all kinds, okay, and of course the library development is linked to the WIF survey operations. As I mentioned before, this is...
Sorry to interrupt, Alex, so 5 minutes?
Okay, I think I can make it.
Thank you.
Thank you. The WIF survey footprint, you can be covering basically all kind of, so it's also covering the streams like Sagittarius, Celadus, and so we will really take this opportunity to have all kinds of stars that our galaxy offers us. Okay, so as I mentioned before, the galactic, the GA survey will offer us millions of stars. Basically covering all from the main supergiants to North, red giants, and so on. From the disk, also about 1 million stars. So we're talking about numbers that is incredible numbers, no? That we never thought about. That Miles is, for example, 1,000. Now we are switching to far more. One important point: if the weather is bad, the focus will be on the low resolution. Now, from all these candidates, according to some estimates, the expectation is that we are going to because we are interested in getting the stars above, with signal to noise above 50, we're going to get the very best. So this represents approximately, the expectation is that we're going to have to enjoy something like 10 to 20% of these millions, let's say, of stars. This is the expectation that can be used for the library. And of course, the parameters will be determined with high precision using the same code as I mentioned. And regarding the flash calibration, first estimate is that we are reaching sort of 7% precision with XP Gaia spectra, and but the idea is to get better than 5%. This is the expectation for the core magnitude diagrams that we are going to get. And another area of improvement is to make populations that are young, in the infrared particularly, and we started these projects, Smarty, this pilot project, and also also the SO Smarty, which has been recently completed, which focused mostly on stars that are hotter than 6,000 Kelvin. This will allow us to provide stellar populations predictions that are lower than 1 gig a year in the near infrared, which is going to be very important for the new observing facilities. And finally, we are also working on extending the models to the far ultraviolet. And for this purpose, we are assembling stars from different surveys in the HST surveys. Okay, and as you can see in this plot, this is the coverage that we managed to assemble so far. This is the temperature versus the metallicity, and dwarfs in black and giants in red. So basically we are covering all kind of stars that we need for the population synthesis. And this will allow us to extend the models down to the Lyman alpha feature at a resolution of 3 angstrom. And all these spectra, we are joining them with the NGSL stellar library that feed our AV-less models, that we ended up having the results that I show you at the beginning of this talk. And this extension is particularly important because it allows us to discuss and to disentangle between the different scenarios that have been proposed to explain the light in the ultraviolet. As I mentioned at the very beginning, having young populations, a tiny fraction of young population, or having, for example, extreme horizontal branch stars tend to produce similar kind of fits. So the question is that the far ultraviolet will probably allow us to distinguish that. Here, just to illustrate, is an example of, for example, you can see here in black a model that is composed of 0.8% of young populations with ages below half a gig a year, plus an old population. Okay, so this is the black model, that the spectrum that you see here, and the different colors, the spectra with different colors, are different implementation of the extreme horizontal branch scenarios. So you can see that, for example, the red line here fits this particular implementation of the extreme horizontal branch is very similar to the one of the young populations. But if you look in more detail, you can see that, for example, here are significant differences. Okay, so these are the differences that, or for example here. Okay, so these are the differences we would like to enjoy or to take benefit of in order to discuss and fit the spectra of the in this spectral range. Okay, so this is going to an important window that is that I hope is going to be very useful in the very near in the next years. And well, just to refresh you with my last slide, with these model developments that I explained you, well, basically working on detailed chemical enrichment. I mean, I'm trying to get better estimates regarding the chemical evolution of the galaxies by implementing new abundance ratio estimates in the library stars that allow us to compute stellar population models with varying abundance ratios. The young stellar, to study the young stellar component by expanding the stellar library in the infrared, in the near infrared, to incorporate hot stars, increasing the resolution of the models, which is going to be a very important, particularly for low mass systems, and opening, extending not only to the near ultraviolet but also to the far ultraviolet our predictions in order to distinguish among the different contributions that shine in that spectral range. And that's it from my side. Thank you so much.
Okay. Thanks so much, Alex. So let me see if I can switch to this. Thanks a lot. Lots of interesting stuff actually there, and especially the last things you have been mentioning. It's really looking forward to all these updates. So I'm just wondering. I mean, we just really ran out of time, but I'm wondering whether you guys here, the ones left, have any questions for Alex. Do you want to? So I mean, while people perhaps are thinking on questions, I was thinking, Alex, when in this image you showed of the work that you did with Adam Knowles and Anne Sampson on comparing with abundance ratio, the MGFE and the MGFE prime, I'm just curious because you know that Daniel Thomas was making a substantial difference, saying this index is very special because it somehow breaks the abundance ratios, whereas it seems like the behavior is very similar. So would you see any improvement of using one versus the other?
Well, no. If you, for example, if we focus for the old galaxies where these effects are more, let's say, relevant, okay? So you can see here, for example, these are, I mean, the color, let me explain to you again. This is in green is the minus 0.7 metallicity, and then black is minus 0.25, red solar, and super solar is blue. Well, the difference that you can see as a function of when you vary the abundance ratio is very, I would say, negligible almost, but I wouldn't say that this index is better than this one.
So they are similar in that regard.
Magnesium iron combine it. And I'm showing you where the differences tend to maximize, okay? And as I said before, is not that the previous, I mean, Daniel conclusion is by any means or wrong. It's just, I mean, these differential corrections, as I show with the H beta, are, I mean, I would say is safer, but they are not completely safe. I mean, it depends on the modeling.
Right.
They will also influence our resulting models. No, as the best example is, for example, here. No,
Exactly. So, I mean, along these lines, I was wondering whether you have thought about, given that you have, at least within the model, the limitations of the modeling approach, whether you have come up with ways of defining new indices that perhaps might be better. I mean, much in the same way as you define the index, the HBO with Cervantes. I was wondering whether there could be the possibility of defining new indices that are more resilient to variations on alpha iron so that you can perhaps use them. I don't know.
Well, here you can see in the far ultraviolet, for example. Yeah, I mean, you are completely. I mean, this is a very good point. No, that all the indices we have been using so far, they are mostly because I mean, they are inherited, let's say, from the, for example, like the leak indices in the optical, but all the indices can be optimized. But it only has been done an optimization for some of them. For example, we have done so in the near infrared in a recent paper, I think 2021 with the Vazdekis et al. And this needs to be done also for the new spectral ranges and of course also in the optical. The here is, for example, okay, as I mentioned before, you can see that there are differences between the young population, let's say a model that has this tiny, less than 1% contribution of young population in black, okay, and if you look, you see, okay, well, this implementation, when the red in this case of the horizontal branch makes similar kind of, but of course there are indices here that they are not similar. Look, for example, here, okay? So these are the kind of indices that should be optimized in order to provide this new means for the fitting our galaxy spectra. I fully agree with you.
Cool. So is there any other question? So I think I'm going to finish with one, and I wanted to ask you, when you were showing this nice plot with the sodium iron, and then you were comparing, and then the giant ellipticals actually, so I think you were comparing the stars, and then you have the giant ellipticals basically sitting on the higher part. I think it was at the very beginning in the introduction.
This one.
And there was, I think, possibly there was another one where you were showing the giant ellipticals that really were standing out at really high values.
Yes, here. For example, you mean the sodium?
Yeah. There you go. That one. Yeah. The symbols are small. Sorry, I missed them. So
these are the giant ellipticals. These
yep.
Triangles.
So do you have any feeling, any thoughts about why those guys are always up there? You know that, for instance, in this business of the IMF, there was always this criticism that the IMF maybe was not really IMF variations, but it was sodium. And indeed, these guys have enhanced sodium. And in globular clusters, they make a big mess of the sodium enhancement, that you have this accreted versus in situ. So do you have any thoughts on this extrapolated in a way to giant ellipticals?
Well, you're right. I mean, in principle, sodium is degenerated with the IMF. I mean, the steeper the IMF, you tend to get deeper sodium features. Okay, I mean, stronger strengths. And the same applies when you increase the abundance ratio. So we have, for example, in a paper that we published, I don't remember, a few years ago, by Francesco La Barbera, we concluded fitting the 4 sodium lines in the optical, in the J band, in the I band, the J band, and the K band. Okay, all together. In this way, we obtained values of the sodium that are lower than if you, for example, the solution was consistent for both the IMF and the sodium abundance. But by fitting so many indices of sodium, we decrease this abundance of sodium slightly, but of course they clearly deviate, as you can see here. This is the solar, more or less, where my cursor is, and you can see that most of the ellipticals are higher. But I mean, you could easily, if you use, for example, other model predictions from other authors, you may get even higher. So this is like sort of, let's say, conservative, And of course, if you go to the ones in the in the dwarf ellipticals, which are these black points, okay, it's lower, or even for example, the red crosses that you see here, or the red X, are the fornax dwarf individual stars. Of course, we are mixing here individual stars with the integrated line, which is not a good, let's say, approach, but it's illustrative, just to see in relative terms, okay? So it's clearly that these galaxies are different, and well, it has been proposed some, let's say, scenarios to explain that, but I don't think, for example, that this trend goes with the metallicity, but I don't think we reached a robust conclusion at this stage.
Okay, thanks so much, Alex. As usual, always a pleasure to listen to your talks on this stuff. So it's really excellent. So we will be putting this together in YouTube in the channel, and thanks so much everybody for watching this talk. So thank you, thanks Alex so much.
Okay, bye.
Thank you. Take care.
Okay,
bye. Of course. Thank you.